In this video, we'll be learning about proportions. In its simplest form, a proportion is synonymous with equivalent ratios. And we already know how to solve these because testing and finding equivalents with ratios and proportions is really the same way we would compare, raise, and simplify fractions. And so to define it simply, this is just equivalent ratios. So how do we then apply the rules that we learned with fractions to ratios and proportions? Since the same rules apply, and it seems a little fuzzy about how that would work. Let's take this example. Is 20 to 30 equivalent to 5 to 6? So one of the things that we have to remember is we make the assumption whenever we multiply or divide a ratio, its equivalent is always the result of multiplying or dividing by 1. That sounded really confusing when I said that out loud, so we're going to look. If we have 20 over 30 written as a fraction, and we multiply it by some number over itself, that's the same as saying 20 over 30 times 1. Remember, n over n is equal to 1 because of the division identity property. So what we're going to do is we're going to test to see if we take 20 divided by 5 and 30 divided by 6 to see if we come up with 1. If we come up with 1, these are proportional. If we don't, these are not proportional. 20 divided by 5 is 4. 30 divided by 6 is 5. Because 4/5 is not equal to 1, this is not proportional. Now, the other way that we could test for proportionality is to take 20 divided by 30 and see what it is as a decimal. And when we do that, we get 0.6 repeating. And if we take 5 divided by 6, we get a decimal of 0.83 repeating. Because those two are not equal, these are not proportional. Let's look at another example. We're going to test it both ways. We're going to see if we can come up with a fraction that is equal to 1, and we're going to test to see if its decimal value is also the same. To do that, we're going to look at 15/5, or 15 to 5. Is that equal to 12 to 4? Let's talk about it the first way. 15 divided by 12 and 5 divided by 4. 15 divided by 12 gives us 1.25. 5 divided by 4 gives us 1.25. 1.25 divided by itself is 1. According to this way of solving, yeah, this is proportional. But let's look at it the other way, because I'm guessing most students, or most of you watching this video, are going to prefer to find their decimals and go from there. And that's fine. We're going to take 15 divided by 5. That gives us 3. 12 divided by 4 also gives us 3. Because these are equal, we just found another way to confirm that, yes, in fact, this is proportional. Remember, the assumption that we have to make is we have either a multiplier or divisor that is equal to 1 being applied to these ratios. And what we just saw there was that there are multiple ways of setting up a proportion problem. And those are just kind of the start of this. What if we have a problem like this? The ratio of a rectangle's length to width is 4 to 3. Find the width of a rectangle if the length is 48 inches. Now I know we haven't covered word problems in too much depth. We kind of saw it come up with the unit rates. Proportions are really just unit rates, are similar to unit rates, similar to fractions. So we're going to look at 3 different ways to set up this problem. The first way that we can do this is we can compare the small rectangle to the big rectangle. So the small length and width has to be equal to the big length and width. Or the way that we can set this up is that we compare large to small in this way on both sides. So then we have large and small. The difference here being that on one side, this would be the length, the other side would be the width. And the way this would look, large, small, large, small. Then last but not least, instead of putting an equal sign in the middle, what if we just tried to cancel out some of these equations? Oh, sorry, not equations, units. What happens if we try to cancel out these units? And we take our large ratio times our small one. So the large length over width times small length over small width. And see what that equals. Now you're probably wondering why I changed how I wrote these. So we had length over length, width over width, length over width times width over length. There, that probably makes more sense now. Let's go ahead and see if each one of these versions gives us the same answer. Theoretically, it should, but sometimes what we think will work in our heads doesn't actually work when we put it down on paper. So for version 1, we said that we're going to take the small rectangle first, and that's going to be length over width. The length over width, small, large. Now the way this is going to look is 4 over 3 is equal to 48 over W. In the last lesson, we learned about different properties of math, and one of them was the multiplication equality property, which tells us if we multiply one side by a number, we have to do it to the other side. So we have 4/3 times W equals 48. And then what we're going to do is use the division equality property to divide both sides by 4/3. W is equal to 48 divided by 4/3, which is 36 inches. And that probably seems like a lot of work. So let's see if we can simplify our work any by looking at length on one side and width on the other, and do the large on top and the small on bottom. So the large length was 48 inches, the small one was 4. We want to know what the large width is, but we're given that the small width is 3. Similar to the last problem, we're going to start with the multiplication equality principle, property, to move the 3. That gives me 3 times 48 divided by 4. When we type this into the calculator, we also get 36 inches. So far, so good. It seems as though both of those versions work. So let's look at the last one. And the last one, we said we're going to take that large one times the small one. So what we have is 48 over W times 3 over 4. Now you're probably wondering how we're going to get the W off of the bottom. And because this would look like 48 times 3 over W times 4, we can pull out the W. This is W times 48 times 3. Sorry, back up. This is 1 over W times 48 times 3 divided by 4. So when we pull out the W, it still has to be dividing by W. And what we're going to do is multiply by W to both sides. 48 times 3 divided by 4 equal to W. And we already said that was 36 inches. So the third version will work. It's just going to be whether or not you prefer it. All 3 of these versions work. Some problems you might want to use version 2 for. Some problems it might make more sense to go with 3. For others, the first one might work too. So it's going to be down to preference and the information that you're given in the problem. Why don't you go ahead and take a moment, pause the video, and reflect over what we've done so far. Now that we're back, I want you to pick 2 of these 5 proportion problems. We will look at the answers later in the video, so go ahead and pause and pick 2 of these 5. If you picked 2 of them, maybe 1 and 4, and they seem too easy, go ahead and do another one. Before we end the video, earlier we said that defining proportions could be thought of as equivalent ratios. But I want to look at another way that we could define this. And that is a proportion is a change in one variable that predicts the change in another. So you could think of this as our complex definition. We are looking at something similar, but in a different way. So let's explore what this means. To do that, we need to review the coordinate plane. In the last video, we also did a small review over coordinate planes. But back in lesson 1, when we looked at it, we should remember that it's made up of an x and y axis. And when we plot coordinate points, we plot them on the x and y coordinate. So if we plot multiple points like we did in the unit rate video, we start to get a trend. And specifically in that unit rate video, we had hours on one side, miles on the other. And when we plotted our trip, we had a line or data in a line that looked like this. When a graph or data plot shows something like this, or maybe it's fuzzier, and you have dots that kind of do this, okay? Both of them have a trend. And that trend is here and here, okay? These represent what's called a direct proportion. As x increases, y also increases. Now, this relationship that we just looked at is called a linear relationship. So this is a linear relationship. Which just means it's a straight line. Now, the other type of direct proportion that you can see is not a straight line. Actually, it looks like half of a U. Okay, and this is usually an exponential relationship. You almost always, when we talk about this type of proportion, we'll be looking at x squared to some degree. X is still increasing, but y is increasing at a rate that is slightly different, but still consistent. Or that as x increases by 1, y is increasing by x squared. And that's what's going to give us this half of a U shape. We also call this a parabola. And that usually refers to when we see the full shape. If we have x and y. Now, there is another type of proportional relationship. If this one is as x increases and y increases, what happens if x continues to increase but y decreases? What would that look like? And what would that be called? These are going to be called an inverse proportion. No matter what, x cannot decrease. It can only increase. If we start over as far as we can, on the left-hand side of the x-axis, we can only move from left to right. Y, on the other hand, as we move from left to right, can only increase and decrease. And it's going to depend on what the value of x is. So the first one is a linear relationship. X increases, y decreases. And the second is an exponential relationship, but it's the other half of the u, right, from that parabola. X is increasing, y is decreasing at a rate of x squared. Before you go, here are the answers to the U-Try problems. Pause the video if you need. Look over these answers, maybe go back and try to figure out how those word problems came out with these answers. And I'll see you next time.